Yeah. No, I got it all. It'll count down.
Okie dokie.
And I'll do an intro. Alrighty, welcome everybody for joining us today. You're joining us for Michael Ridler's presentation on investing in geothermal heat pumps, benefits for utilities and consumers. So, if you're an engineer, contractor, or utility, there's something here for you. So, Ridler, why don't you just kick it off and let's get going?
Yeah, well, obviously, thank you everybody for coming. I think this is like the third or fourth one that I've done with plumbing and HVAC. It's been fun. I've done every topic you can imagine. I think at this point, we've talked about gas boilers, we've talked about air to water, hydronic heat pumps. So I think the takeaway from that is that I'm pretty technology agnostic. So what I mean by that is that, there's a place for geothermal, there's a place for air to air, and there's a place for gas if we look at the market as a Canada-wide market and don't just focus on Ontario. But the goal for today's conversation is spoiler, as Leah pointed out, I'm going to talk about geothermal. I'm going to talk about geothermal in a variety of different ways, but the whole focus of the discussion is just to talk about heat pumps and geothermal heat pumps in particular and what the benefits are to utilities and consumers. And the interesting takeaway is there is equal benefit for both. And that's quite unique about geothermal. You can't say that about air to air or gas. And I just want to, again, reiterate, there is a great place for air to air. There is a great place for gas in Canada as we move towards decarbonization. Less gas is still good in comparison to the gas that we consume now. So from the standpoint of sort of what we're going to talk about today, right off the bat, who is this guy? So I'm Michael. Leah already introduced me. My background is that I've been in the industry now for over 2 decades, which means I'm getting old. The gray in my goatee gives that away. I work with the International Ground Source Heat Pump Association. I work with CIPH on training and code standards. I'm on CSA technical committees, but at the heart, I'm just an HVAC guy. I grew up in the industry. My mom and dad owned the local HVAC company. My uncle owned the wholesaler. So I got to see every sort of aspect of the business. And now I work in specialty distribution. As far as what we're going to talk about today, we're going to do a little bit of a brief history on ground source heat pumps. We're not going to beat that to death, but ground source heat pumps, spoiler alert, they're not new. They've been around a while. They've evolved a lot. We're going to talk a little bit about the evolution of the technology of like how has, ground source heat pumps evolved over the years, because just like boilers have evolved and heat pumps evolved from an air to air standpoint, now we even have air to water. Well, ground source heat pumps have evolved and will continue to evolve. We're going to talk about some innovative and interesting projects, and we're going to talk about some of the motivations of why might we want to do a ground source heat pump. One of the really cool things about a ground source heat pump is a ground source heat pump is something you can install anywhere in Canada, and you're going to get the exact same results if you're in Alberta than if you're in Ontario. And that's really unique, right? If you look at other heating appliances, we need to be very conscious of outdoor design temperature, degree days. And I'm not saying we don't need to look at those things, but we don't have to worry about what's going to happen to the capacity of the equipment, what's going to happen from a peak load standpoint. And so we're going to touch on a few things, but I'm going to try and keep this conversation to a half hour or so, maybe 40 minutes. And so we're going to just touch at the high level on a bunch of different topics. Obviously, if I say something and you have a question about that, Leah's going to be monitoring the chat. She'll gladly throw it out. If you have no questions, I take that as a badge of honor. I've done a great job or I've bored you to death. Somebody else can decide on that front. So as we get going, the very first thing I want to talk about is sort of just a brief history of ground source heat pumps. So ground source heat pumps are not new. The development of ground source heat pumps started in the 60s and the 70s. And I don't just mean from a research standpoint. So there was a lot of research that was done in Europe, but some of the first ground source heat pumps were actually developed here in Ontario. So specifically, there is a Geosolar heat pump, which was a brand that was built in the early 70s. They are still installed. I still run into them this day. Can you imagine having any other heat pump that was installed in the early 70s that's still out there, and there's hundreds of them installed? So you have things like the Bush pump, you have things like the Geosolar pump, and frankly, even water furnace themselves, they have early version SWPR units that have been around since the early 70s as well. So the photo you see on the side is actually the water furnace team. It's the only old photo I have of a geothermal team. And so that is the early days in 1983 of like mass production of geothermal equipment. And I'm a little bit biased because obviously, we distribute their products, but it's a Canadian company, or was a Canadian company at the time. In the 80s is sort of when you started seeing mass production. When you look at the Geosolar and the Bush pumps that came out in the early 70s, I wouldn't call those commercially, I don't want to use the word viable, but they weren't commercially produced. They were a small production. There were many other manufacturers making units. But in the 80s is when you started to see companies like Water Furnace and Climate Master and other leading brands that started actually building large scale geothermal heat pump production to go into the market. The other thing that was really unique is that that's when we started to see an evolution in loop technology. So specifically, we're seeing things like closed loop systems with the advent of high density polyethylene pipe. And so what that allowed is that allowed for more mainstream adoption of geothermal heat pumps. Now in the 90s, as I sort of get to the end of my sort of introduction to ground source heat pumps, that's where the International Ground Source Heat Pump Association came into play. So IGSPA is an organization that is a North American organization, and they're responsible for the promoting and the educating and providing technical training for contractors and engineers. And obviously, as soon as you can have a trade association that's laser focused on that industry, it makes a really big impact on the growth of the industry. And it did drive not only more adoption of residential geothermal systems through education, but it also helped manufacturers improve their energy efficiency and drive energy efficiency programs that focus on geothermal. So IGSPA would be the advocate that's sort of pushing the industry forward. In the early 2000s, we saw some very interesting things happen. There was a lot more research that happened on loop field design. I don't want to say there's, a lot of rules of thumb, but in every industry, whether it's a gas boiler or an air-to-air, the technology evolves over time. And in the early 2000s is where we saw a lot of research and development going into closed loop systems, hybrid loop systems, which we're going to talk a little bit more about. And we also saw a lot of new higher efficiency refrigerants coming into play, and that had a big impact on the COP of the system. We tend to look at, when we look at the COP of the system, we look at things like coil design, compressor sizing. We overlook little things like just evolutions in the refrigerant itself, which makes a big difference. And the other thing that happened in the 2000s is we started to see a really big adoption in commercial. When you look at commercial and industrial sectors, that is one of those sectors where ground source heat pumps can really pay for themselves very quickly. And as you look at decarbonization across Canada, which is something that we're heading towards in 2050, and frankly, a lot sooner, ground source heat pumps are going to play a critical role in that. And frankly, so will air-to-air heat pumps, so will hybrid systems. So whether it's an air-to-water with gas, or for that matter, a geothermal system with gas. And really the most recent, I peg it as the 2020s, but the real evolution right now is energy management and smart controls. The ability for you to put smart controls into a geothermal system for very minimal cost, whether it's a standalone home or whether you're going into a large commercial application, or if you're going into a subdivision with 1,000 homes, smart controls and energy management is sort of that next plateau that we've reached from a standpoint of how do we improve our systems. And later in this presentation, I'm going to share some data, and I was only able to share that data because of energy management. So we'll sort of talk through that. The other thing that we've seen evolve in the last few years is, again, it comes back to that hybrid discussion, but we're seeing ground source systems that are being better integrated with other systems. So we talked about integrating with gas and things like that, but we're starting to see hybrid ground source systems that are relying on solar PV. Some of them are using solar thermal, and some of them are using phase change thermal storage. And I'm going to share very briefly some examples of how that's being used and how it's being applied as we go through today's presentation. So I'm going to talk about some key advancements. I'm not going to get too crazy detailed on this, but when you look at ground source heat pumps and how we've seen the evolution of the COP, so when you look at the COP of a ground source heat pump, you can actually have a COP, and this is ARI data, that drives you as high as 5.3, and that's quite significant. And one of the driving factors behind that is the adoption of variable speed compressors. So you have obviously 2-speed compressors, you have variable speed compressors in some applications, single speed compressors, but the adoption of variable speed compressors is going to continue to grow. And the big advantage of that is that dynamic load matching. It allows the unit to run at and match the load that the building needs. We're not running a compressor at 70% capacity or 100% capacity if we in fact only need 15% capacity. Well, that has a huge impact on the overall COP of that system. That's how you're able to get these really, really high COPs at part load. The other thing that's really interesting in the variable speed compressors from an engineering standpoint is I always use this car analogy, and I know Leah's heard me say it before. If I was to jump in my car and if I was just to redline it and just drive as fast as I could through the city from stop sign to stop sign, I'm going to need a lot of service on my car. Like, I wouldn't recommend driving like that. It's probably really bad. That's how Leah drives. I don't drive like that, for the record. Leah, you're welcome, Leah. She's like, why'd you drag me into this? So a variable speed compressor is sort of like a good driver, right? So we just agreed Leah's a bad driver. She's going to be smacking me next time she sees me. A good driver would be the variable speed compressor, right? So if I'm in the city and I should be driving the speed limit, Leah's going to hate me after this, right? The compressor can run at 15%, 25%, 30%. It's going to regulate its output. And not only does that mean your car is more efficient, it also means you're going to have less wear and tear in your car. So when you look at a geothermal heat pump and you look at a compressor, it's no different. Now, obviously, on top of the reducing of the wear and tear, any time that we can reduce the operation of that compressor, just like your car, we're going to achieve higher energy savings and higher efficiency, typically in the 30 to 40% range. The other thing that we're seeing, and there is a manufacturer that actually just announced this week, it was a couple of nights ago, they announced that they've released a new geothermal unit, and specifically what they're focused on is their heat exchanger design. So they're focused on their heat exchanger design to overall improve the thermal transfer efficiency in those units. And what they're doing is they're trying to draw as many BTUs out of that ground loop as possible by focusing on not just the heat exchanger design, but picking the right compressor. And anytime we can improve the heat transfer process, obviously we're going to result in much higher COPs and much less energy loss during the operation of the unit. So the biggest advancement we're seeing in geothermal is obviously just engineering. There are a lot of really bright minds as geothermal becomes much, much more mainstream, is going to be the term that I would use, because geothermal compared to air is a much smaller segment, but there's some significant advancements that are happening with that technology. The other thing that's made life a lot easier, and this isn't a last year thing, but in the last few years, we've seen a really big in development in loop design. And really where I'm going with this is there's a lot of software that's available through manufacturers that use specific algorithms that'll allow a designer to actually figure out, okay, I'm going to go and do 100 homes. I'm going to do them in Edmonton. They can actually look at the soil thermal conductivity. They can actually go in and size the system using data. You're not basing this off of, I've been a Climate Master dealer for 20 years and I know the area and I know a ground loop should be this size. You can use software to accurately model and figure out what you should or shouldn't be doing. And in some cases, it can make a big difference. If you start looking at hybrid systems like vertical horizontal loop system designs, you can actually increase the overall COP of that unit just by using software and being involved in the design phase and just taking advantage of new technology. Just because you have a lot of experience and have done a lot of ground loops and understand your market doesn't mean there isn't an opportunity to use new software and enhance your knowledge. I know I certainly do as part of my role. Using new software makes a big difference. Now, this is mainly on the commercial side. Now, commercial I would deem to be anything that's a large residential application or a high-rise building. The ability for us to go and do a TRT test means that we can actually go and see that when we do a test from a thermal conductivity standpoint, we can see how many watts we can pull out of that ground loop for every degree of change. So if you go in and if you're able to calculate what is the heat transfer and what is the performance going to be, you can have a significant impact on your ground loop. So for example, if we went into a job and we had thermal testing done, if it comes in at 1.5 watts per degree change versus 1.8 watts of degree change, that can make a difference of 10% in your ground loop design. So having these tests done is something that is really important to be done. And there's a lot of really great companies, certainly based out of Toronto, that do these borehole testings to make sure they're actually doing a high performance building with a properly sized high performance ground loop to support it. Now, one of the other things that's also come into play, and it's certainly not that new, is we're seeing a lot of new grouting materials coming into play. And just to be very clear, I'm by no means saying that, hey, if you're going to use a high performance graphite enhanced grout, you should shorten your loop. I am not saying that whatsoever. What I'm saying is that obviously trust the math, do the calculations, figure out what your ground loop should or could be. But by using a thermally enhanced, like a graphite enhanced grout, you can have a significant impact on the performance of that ground loop Just like if you don't backfill your ground loop correctly, you're going to have negative impacts on that ground loop as well. So materials have changed, and not just grouting materials. There's other technology that we can use. A lot of applications are still using high density polyethylene pipe. Absolutely nothing wrong with that. But now we also have the option to use PEX pipe. PEX is a approved material under CSA C448. It's very nice to work with. It's got great heat transfer properties. It's much more, it is more resilient from the standpoint of, how much you care for that pipe on the job site. Are people throwing rocks and stones on it? I always push back on that statement that if I'm doing the ground loop, I'm going to protect everything. Just like I'm not going to drive my truck into the geothermal unit, I'm not going to mistreat the pipe that I'm burying or putting into a ground loop. So new grouting materials, new piping materials, these all contribute in key advancements that can improve the performance of the system. Now, I touched on this earlier. Hybrid loop designs is a really interesting thing. It can work for you or it can work against you. And so the QR code on the right that I've dumped in there is for a lengthier article that I wrote about this topic. But what we're seeing is, in the most basic way, you can run into applications where you have vertical and horizontal loops. And so what I mean by that is you could go into an application, say you've got a MERB application. We'll say it's a 30-story MERB building and you've got a parking lot out front. So you may go into that and say, okay, we're going to put some of the ground loop underneath the parking lot, but it's not quite enough to take care of the building. So from there, what you might end up doing is, if you have green space next to the building, you can combine a vertical and a horizontal using green space as well as the under the parking lot to sort of cut back on the space that is required. Now, you can get much more creative beyond that. You can also look at doing, okay, we're going to put a ground loop under the parking lot, and we're going to take advantage of another source, whether it be solar thermal or solar PV. So the University of West London, and by West London, I do mean on the other side of the pond, they did exactly that. So what they did was they did a hybrid geothermal system. The idea behind it was to reduce their carbon emissions as much as possible. So they actually tied that to solar thermal panels on the roof. That's the photo you see in the top right. So the idea was that they would actually have a heat sink where they could store the excess heat in the summer, and it would allow them to balance the building's thermal loads. And their goal is, as I said, to cut their actual emissions by up to 75%. Now, obviously, we don't have to look all the way on the other side of the great ocean to see what's happening. There are applications across Canada where people are doing the same thing. They're looking at, okay, let's use solar thermal. Let's connect it to a ground loop. Let's take advantage of the solar thermal storage. Because one of the biggest challenges that we can run into with solar thermal is sometimes when we're producing that solar thermal, we're producing it when we don't need it. So in tying solar thermal to a ground loop, it gives you the opportunity to store that energy. It becomes usable heat that you can use at a later time. Now, obviously, anytime you start combining technologies, whether it's a boiler with a geo or solar thermal with a geo, you want to make sure you have a good understanding of that technology so you don't misapply it. Misapplying the equipment can obviously result in some pretty significant issues that you don't want to deal with. Now, we talked about loop design, and one of the really interesting things that sort of goes beyond loop design is the whole performance monitoring. One of the things that really, really excites me is the ability with a geothermal system for us to get a full, good understanding of what that unit is doing. So there is a variety of them out there. All of the manufacturers generally make their own version of an energy monitoring system. This one in particular captures over 100 data points every 10 seconds, and it will hold on to that data for 18 months. So from the standpoint of you doing performance monitoring and how that comes back to your design, you can put a geothermal heat pump in, and if it's your first or your 100th, you can go back and you can see in real time how that unit is performing. You can see everything from ground loop flow, entering water, pressure drops, refrigerant data, heat of extraction, air temperature into the space. Like, there's literally nothing that you can't see as part of that. So it allows you to provide not only performance monitoring for the building owner, whether it's commercial or residential, but it gives you that opportunity to sort of validate your data. Did we do a good job? Is there something we should be doing on the next one? If we did testing up front, is the real-time data matching the testing? Sort of the next thing that I see that will go beyond this will be the adoption of AI. We see certainly a lot more AI coming into the space, and AI combined with this kind of data is going to make a huge impact from the standpoint of performance monitoring, and not just with geo. I mean, boiler manufacturers, air-to-air manufacturers will also tap into this, and it's a great resource for us to be able to use. Obviously, we can't not talk about new refrigerants. As we all know, the new A2L refrigerants are coming. I'm specifically picking on the 454B. I'm not entirely sure why 454B was adopted over 454C. Somebody who's listening to this webinar that can answer that, send me an email. I would love to know. But typically what you're seeing is R34, R32, and R54B. The big advantage in these new refrigerants obviously comes back to the environmental factor. We want to make sure that we have a refrigerant that's going to be good for the environment. So it has to be environmentally safe, but it also has to be efficient. And so when you look at 454 in comparison to other refrigerants, it has a very low GWP, which is quite helpful. The other thing about 454 is it's mildly flammable is how it gets put to me. You know, when people get worried about 454B, the biggest thing I like to point to is the barbecue on the back deck, right? So if we sort of look at, you know, geothermal systems or air-to-air systems, pick your poison. You know, if you're okay having a giant tank of propane in your backyard, you should be okay having a very mildly flammable refrigerant in your heating system. Will there be limitations on where it can be used? I don't know. Are we concerned about flammability? Clearly not, or we wouldn't be using this technology. The equipment has safeties built into it to protect the system. The coolest thing about the 454B is that in cold climate testing, it is having an impact on COP. So as we see these new refrigerants come out, it's going to make an improvement to the performance of the equipment. Typically over 410A, a 454B adds about 10% of the COP. In the coming years, it'll be very interesting to see what refrigerants we use, but at this point, it looks like R32 and R454B, pardon me, are the refrigerants that we're seeing coming out for ground source heat pumps and other systems as well. So as we sort of look at some of the advantages around ground source heat pumps and why you might want to choose a ground source heat pump, really the number one reason that you might want to choose a ground source heat pump would be longevity. When you look at the actual system itself, some of the things that we get stuck on is if we take a geothermal heat pump and if we compare it to an air-to-air heat pump, usually what comes into play is people look at it and go, why is the geothermal system more money? Well, the geothermal system has an outdoor ground loop instead of an outdoor unit, right? So the air-to-air has an outdoor unit. The ground loop is outdoor. I am by no means going to say they're the same cost. They're not. The difference is that once the geothermal loop goes in, it's going to last over 50 years. When we say that ground loop is going to last over 50 years, that's a low number. There is no outdoor unit for anything. I don't care what it is. I mean, your barbecue is not going to last 50 years. The reason the loop lasts 50 years is because it's high density polyethylene pipe that's been buried in the ground. It's been grouted or backfilled. Nothing's going to happen to that ground loop, period. So the longevity of the loop system is a huge, huge advantage. As the technology advances over the years, what it ends up meaning is that you'll take the indoor unit out, which is not the most expensive part of the system, and you will upgrade that. So in this particular case, what you're looking at is you're looking at a unit that was made in the 1980s. Pardon me, 90s. It's called an AT unit. So you've got a unit that's over 3 decades old. Well, there's nothing wrong with that ground loop. So as new technology comes out, you take the unit out, you put the new unit in. So the other thing I like about the durability of it, the fact that the unit is inside of the building means that from a durability standpoint, the heat pump is going to be more resilient because it's just not exposed to the outside weather. That also means that from a replacement and operational downtime of what's going to go wrong with that unit, there's less issues that come with it. I also love that the units that come out, a lot of them are factory sealed and tested, which is a huge benefit. At the end of the day, if you can get a unit that's like your refrigerator, you take it in, obviously you're not plugging this unit in, but similar to a refrigerator, when you drop it in place, if it's been factory run test, you know that before the unit left the factory, everything is good inside of that unit. And a lot of manufacturers are testing the equipment to make sure that when you get the equipment, it's in good working order. So from a long-term durability standpoint, I think there is no question that a geothermal heat pump is going to last longer than any other heating system. And those of you involved in geothermal heat pumps, you can point to not dozens, but hundreds, probably thousands, I'm misstating that number, of early command air units, early climate master water furnace, long list of units. And at some point, I should put a photo album together of all the old units that are, 50 years old that are still out there, because there are units very old that are out there.
We have a question.
Yes.
All right. The question is, in the UWLS example, is the fluid from the thermal solar panel sent directly into the ground loops, or is there a heat pump transferring that heat energy into another working fluid at a higher temperature that is then sent into the ground loop?
Yeah, so as you can imagine, the nitty-gritty technical details are not revealed in their designs. So what I'm going to speak to is what I've seen in designs, because that is a great question. There is a couple different ways that you can do it. So the most common method, which is what I believe they're using in this application, is what you touched on earlier. They will use a heat exchanger, because they're not mixing those fluids. They will use a heat exchanger to transfer it directly into the ground loop. So from an engineering standpoint, there's a fair bit of engineering that needs to happen to make sure that's successful. The other application that you will see is, rather than dumping it out into the ground loop, is they will have a thermal storage median that they will charge. So if your outdoor ground loop, I'm going to arbitrarily pick some numbers, but realistic ones. If your outdoor ground loop is at 50 degrees and you want to increase your COP by increasing the ground loop temperature, other designs, what they'll do is, if this is the indoor unit, they'll tie the solar thermal to a buffer in the middle. So they'll lift the 50 degrees to, let's say, 70 degrees before it goes through the unit. So you definitely want to make sure it's decoupled for a whole variety of reasons. And you definitely want to make sure that when you tie it together, you're aware of the fact that you could get to stagnation temperatures that could cause problems for the unit. So hopefully I answered that, Leah. And obviously, if there's a follow-up question, just whip it at me and I'll attempt to answer it.
I absolutely can do that. All right, back at it.
So from a residential energy savings, this is an interesting conversation. So if you were to take a ground source heat pump and compare it to anything in the market 10 years ago, ground source heat pumps pretty much clobbered everything that was out there. Now, obviously, with the evolution of air-to-air heat pumps, it's changed a little bit. You used to be able to profess that a ground source heat pump is going to save you 60 to 70%. And certainly that is still the case against traditional heating and cooling systems. There is no question that a ground source heat pump is the most efficient solution, whether it's air to air or other, but you don't want to be laser focused on one thing. If you only look at the fact that, okay, I'm going to save, let's say 25 to 30%, I've arbitrarily come up with a number based off ARI data. So if you looked at a 25 to 30% savings, that's one part of the discussion. The other part of the discussion is the fact that the equipment is going to last 2 to 3 times longer than a traditional heating and cooling system. So the big thing to keep in mind from the residential energy savings is there's a reason that you can count on your geo unit. When you see ARI data for a geothermal system at COP of 4 or a COP of 5.3, that doesn't change, right? Because we have a ground loop. The photo on the right was provided to me by one of my contractors. So that ground loop is buried beneath the ground. The stable ground temperature is typically 8 to 10 degrees Celsius. Well, it doesn't change. So as the outdoor air temperature changes, the air-to-air heat pump's capacity is going to change. And as the capacity changes, so does the COP. So there's lots of great studies out there. I'm intentionally not doing a COP comparison because I don't want to come off like I'm going after air-to-air. You can do your own homework and you can look at what the COP of an air-to-air heat pump is in relation to a ground source heat pump. They're all over the map. The big thing to take away from this is that, unlike an air-to-air heat pump, as the outdoor temperature drops, we do not see an efficiency drop-off and we do not see a capacity drop-off, which is a big advantage to the ground source heat pump. The drawback to the ground source heat pump is not understanding the upfront cost, right? So if you don't understand where that cost is going and what part of that cost is permanent, you have to look at a ground source heat pump, especially the loop investment, sort of like the roof on your house, right? You're going to put the roof on your house, and probably that's a bad analogy because the ground source heat pump loop is going to outlive your roof. Maybe we'll compare it to the house itself, right? That house, that ground loop is going to be there as long as the house is, not so much the roof comparison, probably a poor comparison. But the other thing that you need to do is you have to be honest with yourself. And I do this as well. There is no question that there is every application that I can possibly think of, ground source heat pump is going to be probably the best solution. But it comes down to, what is your best solution? There is a little bit higher CapEx cost up front. So if you can't afford that upfront CapEx cost, or if you can't justify that cost, I understand that. You have to pick the solution that's best for you. The most efficient solution is not always the best solution, but don't dismiss it just because there's other technology out there. Look at it, review it, and pick what's right for your customer, not right for you. That's something that I do here, and that's why we're having this discussion about geo versus other technology. Now, this is the big play. So when you look at who wins when a ground source heat pump goes in, and this is where Leah was referring to the fact that kind of have content for everybody, we're going to have the utility discussion. Because the reality is that if you are a utility and if you are encouraging people to put ground source heat pumps in, every 5-ton geothermal unit that we install is going to save that utility between $6,800 and $64,000 in infrastructure investment. That is huge, and that is only caused by a ground source heat pump. So we talked about this earlier. We're not just grabbing data out of the air. We are going to use real-time data to make this point. So last week, our company had our weekly. Can you imagine if it was weekly, Leah? We had our annual. It'd be cool to do it weekly. We had our annual Tech Talk where we bring in leading speakers. We don't talk about brands. We bring in leading speakers and we look at technology. And so my very good friend Will Lang came in and did an awesome presentation, which I've cherry picked some of the data points because he talked for an hour. And spoiler, I am not going to talk for an hour. You guys have other things to do. So one of the key things that he focused on was how the utility wins. And I wanted to pull some of that data out. So when we say that the utility is going to save between $6,800 and $64,000 in infrastructure costs, you have to say, okay, what does that look like? Typically, when you look at data, it's research data, which is fantastic. So what we ended up having was Will went in and looked at 274 geothermal systems that are installed in Ontario, right? So what we're doing right now is we're looking at equipment operating in Ontario with Ontario conditions using IESO data. So just so you know what we looked at 75 3-tons, 87 4-tons, and 112 5-ton units. So to be clear, once we went through that entire list, we decided, okay, we're going to cherry pick the 5-ton units. It's important to know that what was analyzed was the actual power consumption during peak demand and cooling. The way that we picked out the peak demand and cooling was we made sure that all of the units were actively running. And we were able to do that because we have over 100 data points available to us, which again covers ground loop conditions, discharge temperatures, every single thing that unit is doing, 100 data points logged every 10 seconds, and it's 18 months worth of data. So in pulling all this data together, we're able to see what are these units doing and what is the impact. And so as Will did that analysis, what he was able to do is he was able to sample 100 plus 5-ton ground source heat pump units, and he could see that these units were reducing the peak cooling demand by 3.75 kilowatts. So what that means is it's the equivalent to 0.75 kilowatts per ton to have a 5-ton geothermal unit installed in Ontario. Now, the fun part is you can redo this math. You probably struggle to get the data that we got, but reach out. Maybe there's a collaboration point. But if you look at the average EER, and so it's from 2 different time frames. So one was from June and one was from July. Important to note that we picked the peak cooling time for it. So that is the data point that we have. You can see that the units were 44 EER or 48 EER. When you look at the red box, what that represents is a 1 sigma box curve. And so roughly 2/3 of the units were operating at either 44 or 48 EER. This also means when you look at the graph on the left-hand side, you can see that the average kilowatt consumption for this 5-ton unit during a peak cooling load was 0.28 kilowatts and as little as 0.1 kilowatts. So 100 watts for that geo unit to run. Because this data is collected every 10 seconds, it's a really, really good data representation. So from a consumer standpoint, is this going to mean energy savings? Absolutely, it's going to mean energy savings, whether it's up against an AC, a heat pump, whatever the case may be. So it's going to be meaningful energy savings. And more importantly, they're going to be comfortable, right? You hit a peak cooling demand. You're not going to be concerned about your cooling concerns. And I'm not saying you are with anything else. A properly sized AC or air-to-air is the same thing. I'm not arguing that one is going to be more comfortable than the other. We're assuming everybody on this webinar knows how to size equipment. But the question becomes, what does this actually mean? So when we look at this, we have to ask ourselves, so if we look at other heat pumps at 12 to 14 EER, what is the green section of this graph worth? And typically what we do is we look at the cost of the ground source heat pump, the cost of a traditional air-to-air heat pump, and we look at the difference in that cost and go, what is that worth to me as the consumer? And to the consumer, it is significant, right? We're not talking tens of dollars. It is going to be dictated by where you are. And you will come up with scenarios where what is this worth doesn't have worth to that consumer. There are going to be many applications where ground source doesn't make sense and air-to-air does make sense, but not if you're the utility and not if you're me. I can't think of an example off the top of my head, other than maybe you've got an application where you can't get the ground loop in. That would be a great example where air-to-air makes sense. But when you look at what is the difference of 0.4 kilowatts per ton to 0.9 kilowatts per ton to the consumer, they may not understand what that worth is. But who does know what that worth is the utility. So we pulled some data from IESO just to sort of make that point, because earlier on what I had said to you is that for every 5-ton geothermal unit that saves 3.75 kilowatts, it equates to $6,800 to $64,000 in incremental grid capacity investment. And that is huge. Quite frankly, this is why it is important to incentivize builders to put in ground source heat pumps, because as you build that building, it is a great opportunity for the builder to educate the consumer and install a technology that is going to not add an impact to our grid. Because one of the things we have to think about is we have this great push for electrification. I have no issue with that. I think it's a fantastic thing. But we have to recognize, what if the grid can't support everything, right? So air-to-air heat pump, ground source heat pump, great. Will the grid support it? Will the grid support it if Leah and I and all our neighbors get Teslas, right? So now we all have chargers. Now we all have heat pumps. What does that look like? I don't know. I'm literally saying to you, I have no idea what that looks like, but somebody needs to think about it. So when you look at this equation, what we do understand is that building new grid capacity is expensive. Geothermal systems are going to help lower the cost by reducing that peak demand, which you saw in my previous slide. So if you look at what 3.75 kilowatts equates to, where we get that $6,800 in wind is the capital cost from IESO on the right-hand side. So they're saying the capital cost for them to get 1 kilowatt of wind power is $1,824. Wow, we multiply that out by 3.75 and we figure out, okay, so if we want to power our homes, forget whatever we're doing, we need to have $6,840 invested for 3.75 kilowatts. If we do it with hydroelectric to get 3.75 kilowatts, that means we need to invest $64,511. That's a significant investment. Or you can incentivize consumers to install geothermal systems. And then you don't have to build a new grid, because the geothermal system doesn't have that additional peak demand that's going to come into play. So again, applications where gas makes sense, applications where air-to-air makes sense. There's a whole variety of different applications, but you cannot go into different markets, different cities, different areas, and I'm not saying anybody is, and just go, here is the solution, right? We're going to do heat pumps. We're only going to do air-to-air heat pumps, or we're only going to do ground source heat pumps. No, you have to look at the bigger picture. And to me, one of the things that's really cool is sort of looking at, what does it mean to CapEx? What is the cost if we didn't actually look at geothermal as a viable option and we had to upgrade the infrastructure? So I think this represents it really well.
I'm going to interrupt for a second, Mike.
Yep.
We had a question just before actually you touched base on the utilities. So if you could go back, I think it was 4 slides. One more. I think it was this slide we were at when Max asked. So he said, is the 25 to 30% energy savings relative to air source heat pumps?
Yes. Yeah, that's this slide. Yeah.
Okay.
So if you take the EER data, or whatever data you want, go into the ERI data, and if you compare a geothermal to an air-to-air, that's where that number comes from. And in the past, it was much higher. And the reason that it's creeping closer is because of the cold climate. So where that shows up on the consumer side, but it doesn't show up as much on the utility side, right? That added peak demand. And obviously, as air-to-air technology evolves and as ground source heat pump evolves, it's sort of like this, right? There's a constant evolution and advancement in technology. I can remember where I was. Okay. So As we talk a little bit more about decarbonization, one of the things that really, really excites me, and I've talked about quite a bit, I'll be in Edmonton talking about this topic. So if anybody listening to this is in Edmonton in a week, I think, love to sit down, talk to you, and sort of go through this entire presentation. What I find exciting about decarbonization and PCM is the ability to store BTUs and not watts. So when I say PCM, I'm referring to thermal storage. I am particularly picking on phase change thermal storage, but there is other available thermal storage out there. You will see a variety of different types of technology. I'm not going to drop name brands here, but if you look at the brick-based systems, they typically operate at 300 degrees. You put them into your home, they can thermally store energy. You have sand-based systems, so sand-based systems are taking advantage of the specific heat of the sand to store energy. What I particularly like about a phase change battery is it's taking advantage of sensible and latent energy. And I'm not going to spend any amount of time on that. There is lots of other videos I'll be talking about it. Go watch one of them. But the biggest takeaway is that we can store a lot of usable heat at very, very low temperatures. So to give you an idea, we can store 4 tons of capacity in basically the size of a very small filing cabinet. And Leah and I were on a site not too long ago, and we filmed that. That's available on the Plumbing and HVAC YouTube channel. We can store BTUs in a very small footprint, but what's really, really cool about it is you don't need high temperature. So you can actually store the energy at 120 degrees, 140 degrees, very, very low temperatures. So the reason I'm focused on this is because we get really concerned about end-use energy consumption, and I'm all for that. But if you actually look at a single-family dwelling or a MERB application and go, where is the bulk of that usage happening? Well, the bulk of it is happening on the heating side, right? Like if we look at what we're doing, we're heating and cooling our homes. And the challenge that we run into is, well, we can't stop heating our homes, right? Like we couldn't, for example, say, I'm going to put a heat pump in, but to save money, I'm only going to run it off peak. Okay, so what stops your house or your building from freezing when you're not running on peak? And that's kind of the holy grail to it. So what I really like about the concept of doing thermal storage is it allows us to actually store that usable heat to use it later. We can do it in a very small footprint. It's commercially available. And again, it just comes back to this whole concept of storing BTUs and not watts. What I like about PCM and its decarbonization play is not just the whole storing of BTUs, but I like the simplicity of it. There's no moving parts. There's nothing complicated to it. It's just basically a box filled with phase change material that a variety of different people manufacture and put in the market space. And it allows us to store BTUs for later. So what that does mean is we can get into scenarios where we literally can run the heat pump off peak, store the energy, and use it on peak, which makes for a really interesting discussion. So what I like about ground source heat pumps, and specifically in a water-to-water application, and I'm going to share 2 real-world examples of it, is it allows us to sort of take that curve out of it. So if you look at the graph on the right-hand side, that's a photovoltaic yield graph, right? So we're producing all this energy that we may or may not need at that time, and we're storing it in electrical batteries. I have no problem with that. You could actually say to me, Mike, why would you not use an electrical battery, store it as watts? Why would you store it as BTUs? Well, it goes back to my previous statement. If I store it as BTUs, it's a box that has 4 pipes to it and no moving parts. If it's an electrical battery, right off the bat, it's going to be 3 to 4 times the cost, and it's got a layer of complexity to it. Nothing wrong with it. It's a different solution. What's new and unique about a phase change battery is we can take all of that energy that's being produced when it may not be needed. We can store that in a thermal battery and we can use it later. So what's really cool about that, so from a reducing peak load standpoint, is that if we wanted to say, I'm going to put a heat pump in, water-to-water geothermal, and I would counter and say it could also be an air-to-water, we can run that air-to-water off peak, take full advantage of the low utility rates, in Ontario as low as 2.4 cents a kilowatt, store it in the thermal battery, and use that battery when it's on peak. So reducing peak load is fantastic. It also means we're reducing emissions. Obviously, beyond integrating with ground source, we talked about a PV integration. And the big thing to me is that whole support for renewables. As much as we're talking about ground source heat pumps here, walk away from this conversation and think about, how could I use an air-to-air heat pump? How could I use solar PV? How could I use a phase change battery? How could I use gas in combination with an air-to-water? I'm not trying to make it sound like we're only all in on one technology, There's a bunch of different technologies that can provide a variety of different solutions.
I have a question.
Yes.
So we have a question in the chat. So it says, from how long ago do the wind and PV CAPEX, I don't know if that's the right pronunciation of that, it's a new term to me, equivalence date from or on what PV conversion efficiency is its equivalent base? PV efficiency seems to increase every month.
Yeah, so totally agree. One of the things I love about solar PV is one day I'm going to be able to put it on my house. I'm an absolutely huge fan of solar PV. Remind me to come back to the CapEx conversation. I'm going to take the second one first. From a solar PV standpoint, what I really like about it, and I don't have a photo of it here, but if you reach out to me after this presentation, I can share an article I wrote for Plumbing and HVAC. I love solar PV because of the fact that the efficiency is improving and the costs are coming down. There is so much cool solar PV technology coming in the market. It really, really excites me. Solar PV in relation to a phase change battery to me is an absolute game changer. I love the idea, instead of putting in solar PV to worry about all my LED lighting, I go back to this slide, right? I look at this orange. I want solar PV on my house so I can charge my thermal battery. Am I going to use it for other stuff? Maybe, right? I might put I'm a name brand because I don't know what. I might put a Tesla Powerwall in. I don't know. But I'm not really focused on the other consumption. I'm worried about what is the actual heating consumption. To your first question on the CapEx costs, according to Will, he took the CapEx costs directly before our meeting on Friday. So I would assume they're the latest edition of those CapEx numbers. Now, as we get back to sort of the discussion around phase change, specifically with PCM and with geothermal, so what this is this is a MERB application. This is a high-rise building where they're using geothermal to heat the space. They have water-to-water units in the suites. So you can see this water-to-water unit here. And to be very clear, I had no involvement with this project. These are not my products. I'm just talking about it because it's cool. So water-to-water unit, I believe, is sitting right here. And this is the PCM battery in the back of the suite. So the idea behind this is that the water-to-water unit is charging the PCM battery, in this case, for domestic hot water for the building. This is a closer shot. So every single one of these suites has its own PCM battery. There's a ground loop that runs, I'll use my hands or I'll go back to the picture. There's a ground loop that runs all the way up the entire length of this building. And then they come off into water-to-water units in each suite that's doing heating and cooling and taking care of the PCM battery from a domestic hot water standpoint. So when you look at this, they touch on a lot of different things. The PCM battery internally has no moving parts. There's no fire risk. There's no Legionella risk because there's no water stored in it. There's a very, very small amount of water similar to a tankless. There's no maintenance. And what's big in this particular application is in this MERB building, there is a requirement that if you do not have hot water for your tenants, you got to put them up in a hotel. It's a hot water requirement, not a heating requirement, which to me is weird. I'm like, I would think it'd be a heating requirement. So it allows them to, should there ever be an issue with the equipment, that they can still provide domestic hot water into the space. Obviously, the other really cool thing about the PCM battery, coming back to the earlier commenter's comment, is that as we sort of find this path to zero with decarbonization, there is technology coming into Canada where you can actually replace the glazing on the outside of the building and it becomes your solar PV. So what happens if that happens? Well, no problem. Tie that into the PCM battery. The PCM batteries actually have a just under 3 kilowatt element in the bottom that you can charge the actual battery itself, and it doesn't need the water to water at all, right? So there's a lot of really cool applications that come into that. They've predicted that the savings per tenant per suite is $393, and the actual CapEx savings for the actual landlord itself is $2.82 million. I've actually reached out to get a better understanding of the CapEx savings. I just didn't hear back in time for this webinar, but Leah has asked me to write an article about this. So by the time I write the article, come back, I will have more details on that project. As I say, it's not my project. It's just a cool project, and I like to talk about cool stuff. This is another really interesting one, and this comes back to my conversation about utilizing other options. So in this particular case, the far left-hand photo you can see is a water-to-water unit. So this water-to-water unit is being used for domestic hot water. And so what it's doing is it's going into these phase change thermal batteries. This gives you a really good understanding of how small these are. So if you look here in this photo and you see this gentleman standing here, we don't actually know how tall he is, but you can see the water-to-water unit comes just above his knees. And you can see that the phase change battery is about a foot taller than that, right? So if you look at the average male height of being around 5'9", you can see that the batteries are not very tall. When I'm standing next to the battery, and I am 5'9" for that record, the battery basically comes up to about here on me, right? So it's not very big. So what they're doing is they are charging, and again, not my project, had nothing to do with it. These 3 phase change batteries are being charged by the water to water when it can do it. So if this water to water geothermal unit has to heat the building or do cooling or do something else, well, when it's done doing that, it can charge these 3 compact phase change batteries, and they're not actually trying to charge them to produce usable heat for domestic hot water. They were really smart about it. They kept these A.O. Smith cyclones. So the idea behind it is that what they're going to do is they're going to charge these to 120 degrees. So instead of the natural gas appliance having to lift it from 55 to whatever the temperature may be, 160, 170, whatever you're charging it to, you're starting at 120. So this is an application where we typically would do a water to water with a gas boiler, same concept. Well, these people have gotten way smarter about it and said, we're going to use water to waters. We're going to connect them to phase change batteries, and we're going to dramatically reduce the domestic hot water consumption, and they can use the water to water units for heating and cooling in the space. The challenge with a water to water in a domestic hot water application is it's kind of like a Kia versus a Corvette. So it's like Mike driving, I'm the Kia, and Leah's the Corvette. So
I like this better. Thank you.
Yeah, this is a better analogy. So when you have gas domestic hot water heating, it generates a lot of energy, right? Like we can heat hot water very, very quickly. A geothermal heat pump can still do it. It's just not going to do it as quickly. So what you're seeing happen here is they're being very smart about it. The water to water charges the PCM batteries at a temperature that's very easy to do. Each one of these units is capable of carrying 4 tons of capacity, and then they're using that as a pre-charge for the gas. This to me is a great application utilizing multiple technologies. So for example, if you're in Western Canada and you have grid strain, I believe some areas of Western Canada do. We've all seen what has happened there. That would be an application where you say, okay, I get it. We've got, I'm going to pick a number, 5 of these in the building. We are going to offset 2 of them, offset 3 of them, cut our gas consumption by 40% by using phase change, by using geo, whatever their configuration can be. That's what I mean when I said earlier in the presentation that we can't pick technology for us, right? Clearly, I'm a fanboy of all technology. Like I'll talk about air to air, I'll talk about geo, I'll talk about boilers. I love all of it. What is the best technology for today's discussion may not be the best technology for your building, right? Geothermal from an efficiency standpoint is the most efficient. If you can't put it in the building, it doesn't matter. That's where you can start looking at, okay, why don't I use phase change batteries? Or better yet, I can fit geo, but if I need 10 tons, I can only fit 5 tons. Great. This could be that story too. This unit, based off its footprint, could in fact be a 5-ton unit. So they have 5 tons of domestic hot water into a phase change battery, preheating these units. We could skip the phase change, right? You could have the geo unit pre-charging the gas. What I would suggest to you is they're using the geo unit to take advantage of off-peak rates, because we can charge these phase change batteries. And the design of these phase change batteries is when you store the BTUs, they stay there. It's not like a water-based system because it's using sensible and latent energy. So that's big. That's a really nice advantage for us.
We have another question.
Yes, Leah.
Are they already selling the, I believe this should be unique PCMs in Canada, or those residential buildings overseas?
Yes. So they are available in Canada. They're available in the United States. They're available in Europe. You would not be a guinea pig in installing them. Full disclosure, we do rep a product. I'm intentionally not mentioning it. This is not an infomercial for me, although I am wearing my Eaton shirt. I just realized that. You know, my whole point in this is to talk about technology. There is tens of thousands of them being installed in Europe. Here in Canada, we're doing small scale. We're doing, by small scale, I mean little units the size of a microwave that can go into a suite, up to units that are designed to store 300,000 BTUs. And the units are not that big. I believe Leah's seen the larger unit. It's not very big. But yeah, they are available across Canada. Obviously, if you go on the Plumbing and HVAC channel, there is a video. I'm sure Leah can send the link into the chat if you guys want it. It's been watched a lot, which lets me know a lot of other people are really interested in the technology. But at the end of this, if you have questions, Leah can share my contact information. I'm going to sort of wrap things up, but Leah's like, no, we have another question. Yes, Leah.
No, we don't have another question. That was a thumbs up. I did want to let you know we have just over 5 minutes though, so you're getting your little warning.
Shockingly, I went long. Usually I'm done
Oh,
early, aren't I?
that doesn't sound
So
like you.
lessons learned. I'm not going to go through everything too crazy. So as we look at ground source and lessons learned, the number one is just do the proper assessments, right? If you're doing a ground loop, don't do rules of thumb. Take advantage of TRT. Figure out how many watts per degree you can get out of that loop. Make sure you're sizing things properly. Take advantage of new technology. Don't be afraid to try new enhanced grouts. Do some research first. Talk to some friends. Talk to IGSPA. Talk to HRAI. Talk to OGA. Take advantage of new piping materials, as long as they're approved, right? So if you want to try PAX, try PAX. It is a really good solution. It's more money. So people say, I'm not going to do PAX, I'm going to do HDPE. It's more money. There's a difference. There is an advantage, just like with ground source heat pumps. They are more money, but there's a reason. The other thing is be creative in how you do it. Urban areas are not areas that you can't do geo. Don't get stuck in your head that just because I live in the city, I can't do geo. And the other thing is, don't be afraid to incorporate things. Don't be afraid of solar PV integration. Don't be afraid of solar thermal. Certainly don't be afraid of phase change integration, but understand the limitations of the technology and of your own knowledge and tap other people to help you as need be. Obviously, look into monitoring controls. The control I showed you earlier, I love it. If I ever have to troubleshoot a unit, I don't need a tech on site. I can tell you what's wrong with that unit. I've got 100 data points every 10 seconds for 18 months. And then as much as the equipment is very, very low maintenance, which is a true statement, especially when you have the monitoring of it, plan for maintenance. It's kind of like your car. You can't not do anything to it, right? Always plan for maintenance. And the last thing I want to touch on is just compliance. Make sure you take the time to get IGSPA certified. Go to the training, know what you're doing, understand CSA C448, understand the regulations and incentives, and come to things like this. You're going to meet great people, go to the conferences, stop people, ask questions, be engaged. As far as the utilities, I'm going to move past that. I think we already beat that to death. The utilities, from the standpoint of ground source heat pumps, it's great for consumers, but it's amazing for builders. It's amazing for utilities. There's lots of opportunities. And on that note, this QR code will give you my LinkedIn, so you can hit me on LinkedIn, send me a message. If you need my other contact information, Leah will gladly share it with you. If there's any other questions I didn't answer, I'll answer them. If not, it was fun.
We have one more in the chat right now. So Frank says, not a geothermal guy, but I hear the most heat you can heat a home to is 65 Fahrenheit. Is that correct?
That is a absolutely wonderful question, because that is absolutely not true. So just like any piece of equipment, it needs to be sized appropriately. So if you cannot heat the home past 65 degrees, what you're defining is a piece of equipment that has not been sized correctly. So where I'll go with that is that if you look at the ARI data for a piece of equipment, if it's a 5-ton geothermal equipment, just like a 5-ton air to water, it's 5 tons, right? What will typically happen is people will go into an application and they won't understand the intricacies of the ground source heat pump. And specifically what I'm talking about is they won't size it properly. But that's true for air to air and boilers as well. And that's where you start to run into comfort issues. But sizing of ground source heat pump technology is not hard. If you have a good distributor, they should be able to help you size that equipment properly. You don't have to worry about outdoor drop off in temperature. But where you say the house is only getting to 65, you're describing a home where either the equipment's not been sized properly, or better yet, they've done if it's 3 fingers from the road that covers the house, it's a 3-ton. If it's 4 fingers, it's a 4-ton. I'm sure some of you get that joke. Equipment, whether it's geo or otherwise, has to be sized properly. One of the things to be very, very conscious of, though, is the exergy versus energy conversation. And where I'm going with that is what people will say when they put a geothermal system in. And it's the same thing with the air to air in my house, right? I have an air to air heat pump because in my city, they do not allow geo, which is a conversation for another day. The air coming out of my ducts is cooler. There's nothing wrong with that, right? Unlike with a gas appliance, it's not heating the air temperature to a crazy, crazy temperature, but you don't need that. So usually what we will hear is that the house is comfortable. It's at 68 or 70 degrees, whatever the design set point was, but the air leaving the vents is cooler. It's not a concern. It's not a big deal. So to me, it's a sizing issue. If you have the actual details on the project, love to have a look at it. If I can loop you in with a local expert, I definitely do that. I know quite a few people across the country, and in various aspects, I'm sure I'd be happy to help.
I can't believe I'm saying this, but we've timed this absolutely perfectly. We have 20 seconds left before the broadcast ends. So wonderful. So if anybody has any questions, feel free to reach out to Riddler. He'll has no problem answering them. Otherwise, this presentation will live long on our YouTube account. I'm going to do a closing remarks very quickly in the closing marks. So I'm going to have to exit this one and then go into the next one. Otherwise, thank you everyone for joining. And as always, Mike, thanks for an amazing presentation.
Thanks, guys. I can't believe we finished on time.
I know.
Take care.